So in this section, you need to know that the current flowing in a wire carries a magnetic field, and the shape of the magnetic field is given by circles. If, for example, the direction of the current was into the page or into the board, you hold your thumb downwards and your fingers are going to point in the opposite direction. So your fingers are going to point right now in the opposite direction. As you go closer, the wires are going to be, or the magnetic field lines are very close, but as you go further, the distance increases and the distance increases more. Such a question of drawing the magnetic field lines carries 2 to 3 marks, okay? One is for recognizing the shape. If you draw circles, you get 1 mark. If you know the direction, you get the second mark. If you make sure that the distances are not the same, you get the third mark. But if you drew same distances, you just might get a 2 out of 3. And this is the main idea, and this is how you draw field lines around a current carrying conductor. Okay? To increase the strength of the magnetic field, you can increase the flow of current. So more current means more magnetic field. All right? So before we move on, did you get what I just did, all of you? How to draw the patterns of a magnetic field around a wire. Was that clear? Faster. All right. Good. Let's move on. If you have questions, please ask. Moving on. Now, to increase the magnetic field further, we can wind up the wire into a solenoid. Now, a solenoid is a coiled up wire. So if we coil up the wire, we can increase the strength of the magnetic field, because a coiled up wire means more current flows in this section. All right, so more current flows means more magnetic field. So how can I prove that more current flows? Because the longer the wire, the more the current in the wire. So a coil is a longer wire, so increasing the length of the wire increases the magnetic field. So two things: increasing the current increases the magnetic field, increasing the length of the wire increases the magnetic field as well. Okay? So if the current is flowing in this direction, okay, this is going to be the North Pole and this is going to be the South Pole, and it goes from south to north. I think we discussed this in Lenz's law when we were talking about Lenz's law and electromagnetic induction. Cool? Increase the current, increase the number of turns. Alright, applications of electromagnets. I don't know if we talked about that, but electromagnets are magnets that can be switched on and off using electricity. So I think we talked about it when we discussed car scrapyards. We discussed circuit breakers, and we discussed door locks. All of these are applications of electromagnets. So let's see. An electromagnet, and this is a relay. A relay uses an electromagnet. Let me just ask you guys, did we talk about electromagnets and relays before? Did we? Hello? Anybody? Guys, can you hear me? My voice is not clear. Okay, let me see if it gets better now. All right, can you hear me better now? Let's try. I just switched the networks. Can you hear me better? Nujud, Malak, Dana. Can you hear me at all? You still can't hear me, Malak? What about the rest? Sama, Thuraya, Lena, Hassan, can you hear me? Okay, Sama can hear me. Good. Lena and Hassan. All right. I hope it gets better. I hope it gets better. Uh, it keeps lagging a bit, but it's manageable. All right. I'm glad. Just try to, if you felt that you're missing something, just try to let me know. Try to let me know so that I can keep up. I can see which network is better and yeah. All right, guys. So what was I talking about? Hold on, let me just charge my laptop. Just give me a second. Just a second, guys. Mm-hmm. Hold on. Just a second, guys. Now it's starting. Cool. So. Alright, so the lesson got interrupted a little, but let's keep going. Alright. So my question was before the lagging. Did we talk about relays before? No idea. Okay. If we didn't talk about relays, let's just explain what a relay is. All right, for example, I'm going to have a battery, and in the battery, I'm going to have, okay, and there's gonna be a switch here, and there is another circuit, okay, and there is a contact here. These two contacts are not connected, and here there is, let's say, a lamp, and there is a mains supply. Okay, this arrangement inside the box is called a relay. How does a relay work? A relay works when switch S is closed, when S is closed. That's step one. When S is closed, this electromagnet gets magnetized because current flows through it. It becomes magnetized. I'm going to call this C, where C is the contacts. So it pulls the contact together. So it joins this gap. When the electromagnet works, it creates a magnetic field. Okay, this first contact is fixed, the second contact is free to move. Okay, we call this a springy contact. Okay, the springy contact is free to move, so it's like a spring. It connects. When it loses its magnetism, it disconnects back. So it connects and it disconnects. So the idea is, when a switch S is closed, the magnetic or the electromagnet creates a magnetic field. The magnetic field pulls the contacts together, and current flows in the second circuit, and the bulb lights up. When switch S is opened, the springy contact comes back to its original place and the bulb closes. This is what a relay does. A relay connects two circuits, circuit 1 and circuit 2. It connects them, but it doesn't connect them electrically, it connects them magnetically. The current in circuit 1 does not flow in circuit 2. Each circuit has its own current. For example, the current in circuit 1 can be, I'm just going to use random numbers, 0.5 amps. And the current in circuit 2 can be 15 amps. It's totally different, but it connects the circuits using this small device, which is called a relay. But why do we need a relay here? We need a relay to connect two circuits together such that the current in the first circuit does not flow in the second circuit. That's the main function. Why don't we need the currents to flow? Because the currents are totally different, and the first circuit might have certain appliances that can be damaged if too much current flows through them. So we need the two circuits to be we need the two circuits to be separated from each other. So the first thing about relays is that relay is a current amplifier. Amplifier. What does amplifier means? It increases the current. It just uses 0.5 amperes to connect the circuit with 15 amperes. So it amplifies the current. Okay, that's the first thing about a relay. How does it do that? Again, this is just the drawing of a relay. It's a better drawing than my drawing, but it looks like that. First circuit connects the switch, electromagnet gets magnetized, it pulls the contacts together, and the lamp lights up. Spring is steel because the contact moves back and forth. If the switch is open, it loses its magnetism, the springy contact disconnects, and the bulb does not light up. So this is a relay. Why do we need relays? Again, as I said, because it's a current amplifier, it amplifies the current. 2, because we don't need the current in the first circuit to flow in the second circuit. Alright, we need each circuit to have its own current supply. A relay uses an electromagnet, but by now we know what an electromagnet is, because an electromagnet is a magnet that can be switched on and off by using electricity. When the switch is closed, the electromagnet gets magnetized. When the switch is open, the electromagnet loses its magnetism. So it's a magnet that can be controlled by the flow of current. Okay, so this is what a relay means. Alright, so this is how a relay works, and this is the function of a relay. Okay, what else do we have? So let's see. We have good questions here. Alright, so which rule should you use to find out the direction of the magnetic field around a straight wire? We call it the right hand grip rule, and here it says that the corkscrew rule. That's another name for it, but I didn't explain that because it's not in the syllabus, but it's called to find out which way the magnetic field turns. You use the corkscrew rule. A person holding a wire with the right hand. So it's just, I just want you to use the right hand grip rule, but in this book it says the corkscrew rule. Alright, let's see the second question. Alright, a DC is supplied to a coil. What effect would this have on nearby steel paper clips? A DC is supplied to a coil. What effect would this have on nearby steel paper clips with raise of hands? Guys? Najud?
I think 3.
3. They will get attracted. Okay, good one, Najud. An AC is supplied to a coil. If the north pole of a bar magnet is close to the coil and free to move, what would you observe? An AC, not a DC. An AC is supplied to a coil. If the North Pole, okay, let me see. Okay, Nujud, yours your hand again.
1.
The magnet is repelled. Okay. Why will the magnet be repelled? Maybe it's attracted. Or maybe nothing happens. Because repelled, let's see. No. We have 3 more options. Remember AC. AC does not give you a constant magnetic field. It gives a changing magnetic field, like pushes and pulls, pushes and pulls. That's how an AC supply gives you a magnetic field. Because if you think about it, if we connect, let me just go to this. If we connect a wire, a coil, to an AC supply, okay, every time it changes, for example, if this is the north and this is the south, it keeps changing. Now it changes the south and it becomes a north, north, south, south. It keeps just flipping the magnetic poles because it's an AC supply. So if I put a magnet close to here, let's say north and this is the south, and it's free to move, what would happen to the magnet if this magnetic field just keeps changing? What would happen to the magnet? If you have to answer, just say it. What would happen to the magnet? Anyone? 3. The magnet vibrates forwards and backwards. Yes, correct. Okay, a DC is supplied to a solenoid from a hidden supply. Which piece of equipment would allow you to work out the direction of current flow? Okay. Sama?
The compass.
The compass. Yes, compass is correct. Alright, the last part of magnetism is a force on a current carrying conductor. Alright, let's have 10 minutes and then we will